Let's do an example of using total differentials to approximate actual differences in a given function. So if I have a given function, x squared plus y squared, z equals x squared plus y squared. So if you remember what the graph of that looks like, that's the elliptic paraboloid. And so, it's an elliptic paraboloid. We want to be able to say, okay, if I take a function value at a point and a function value at another point, let's compute the differences of those functions. Let's determine what those increments in x and increments in y actually are. Let's use that total differential approximation, what we derived earlier. So let's approximate, instead of computing it, let's approximate it. And then let's compare the actual value with the approximation. So I want us to kind of take a multi-stage process and see how far off we are with the approximation versus computing it straight out. So the first thing is finding f(1). Not too bad. F of 2.1, 1.05. Going to save you a little bit of effort here. $5.1025. So, let me check my notes here. Yeah, 5.5125, sorry. So that's the difference, the change in z, we'll be able to figure out pretty easily. $0.5125. So that's our change. Now what we want to do is we want to find out what those increments are. So all the increments are the changes in x and the changes in y. So our changes are simply the differences here and there. And recall that, well, there's not really a recall situation, but we're going from this point to this point. So in this particular problem, we didn't really say which one was first, but for the sake of simplicity, we're going to say this is our starting point and this is our increment, which is only kind of natural because these are easy numbers to compute and these are not quite as easy numbers to compute. So our x increment is 0.1, our y increment is 0.05. Now we want to approximate delta z with the total differential, but to do that, we need to get some information. We need fx and we need fy. So fx is the partial derivative with respect to x. So the partial derivative here, that's 2x. Y is a constant, so that derives to 0. The partial with respect to y is 2y because that's treated as constant. Derivative of a constant is 0. That's 2y. We also need to evaluate the function at that point. So the values are 4 and 2 respectively. Now to get back to the problem at hand, we have this formula. We say delta z is approximately fx at 2, 1 delta x plus fy at 2, 1 delta y. So again, that's approximately 4 times 0.1 plus 2 times 0.05, which that itself is actually, this is an equality, but we're keeping the approximation just because ultimately it's approximately delta z here. 0.4 plus 0.1. So delta z is approximately 0.5. So by using the total differential, we get we approximate that increment of z as 0.5. But if we compare it to what the change in z actually is 0.5125. So to compare that, we say, your difference of the increment and then the approximate version of that is 0.0125. So a relatively small number. You're talking second digit here, and even the second digit is pretty low. I use the absolute value here because, generally speaking, when you're computing these kind of residual errors, you want to use the absolute value because you want to see kind of the distribution. Now, there's perfectly good reasons to do the distribution on the negative and the positive side as well. One of those is if you're constructing like a histogram of values, you might want to verify that your approximations happen equally to the left or to the right of your mean or true value. If they don't, and you notice they're always biased a certain way, sometimes that's actually good. It tells me that I can always expect that my estimates are overshooting the value versus, you can look at the distribution. But oftentimes they're either stored as magnitudes or sometimes magnitudes squared because they get that way they don't end up accidentally canceling each other out if you do something like a mean. So there's something called a mean absolute error, where you take this absolute error, you take the average of those absolute errors, and that gives you a metric on how good your approximation is. Anyway, I could go on. But another thing so this may say, oh, well, that's pretty small. Well, who cares? It's a small error. The other thing you really want to look at is the relative error. So this is what you would call the absolute error. Basically, how different are they in terms of subtraction? But then the relative error says, how different is this value relative to that value? And I'm going to do something that you don't really normally do. You normally take this value as your base, or as your denominator, but I'm going to do this one as a denominator because the math comes out a little more cleanly. So if I say the ratio of the true value to the approximate value, so if I do that number, so if I double both of these, I get 1.025. So that tells me that there is, in terms of, so if that ratio is 1.025, then that tells me that there is a 2.5% change. So, right, because you would subtract 1, and then you would say 0.025 is actually 2.5%. And if you have a 2.5% change, why does that matter? Well, when you have two very small numbers and you subtract them, you're going to get a very small difference. but you might want to know what the percentage is, because if you are doing this for many numbers, thousands, hundreds of thousands maybe, and you have small errors that accumulate over time, well, that percentage drift can actually take you pretty far off where you were before. So this is actually a pretty high error, I'm not going to lie. 2.5%, it would not be considered an acceptable amount of approximation error for a lot of the simulations that you might encounter where you're taking time history data of like trajectories of objects, and you say, oh, well, I'm only like 3% off. That's pretty bad, actually. Usually you want it to be sub 1%, ideally sub 0.5%. So be careful when you look at errors as to, relative error a lot of times is a better way to approximate. So what I would say is this approximation is actually not very good for this. So if I were trying to approximate again, I might take a step size that's significantly smaller than this. I might try 2.01. 1.005 and try to see whether or not that gets a much tighter, much cleaner approximation.